Hi, everyone, and welcome to this CEDIL webinar today. The topic of today's webinar is a comparison of the validity or reliability of observational studies and randomized control trials. And the title is precisely how reliable are observational studies in practice, using evidence from and data from randomized control trials. And our speakers today are Gharad Bryant, who's an associate professor at the London School of Economics, and John DeQuitt, who's is assistant professor at the International Institute for Economic Studies at the University of Stockholm. And unlike other seminars today, we're not going to have a discussant. So we will just have a presentation, which means that there will be more time for questions, for addressing questions from the audience. So we encourage participants to type their questions. So we won't allow participants to speak directly, but you can please do type your questions in the Q&A box at the bottom. And we will address your questions at the end, preferably. I mean, if in case there are many questions, we can address some of the questions typing back, but otherwise, we will try to answer your question at the end. So we will have some up to maybe 40 minutes presentation, and then we will have some 15-20 minutes for addressing your questions. And before we start, I have to remember that the event is recorded, and that this event is brought to you by CEDIL program. CEDIL program is funded by FCDO and with budget with funding from the UK aid. I think with this, I will leave it to our presenters and starting with Gharad. If you would like to share your screen, over to you. And we're all looking forward to hearing your presentation. Thank you. We can't hear you, Gharad, because you're muted. We can't hear you.
Thank you for having me. I think I would have worked this out by now. Thank you, Eduardo, for the introduction, and thank you to CEDIL for and FCDO for the funding. This is a joint project with a lot of people who you see on this starting slide. Okay, so I'll change screens. Okay, so as a little bit of motivation, we're going to start with a caricature of policy making, which motivates the approach that we're taking here. So I want you to think about a policymaker, and they have a large observational data set. So you might think of a setting in which you have some administrative data. So you can collect on a treatment group, someone who took up a program outcomes, and you also have a reasonable control group also in that data set. And you can use some method to come up with an observational estimate of the program's impact, which we're going to call beta hat. And then we think of the policymaker as taking the following approach. If beta hat is positive, statistically significant and large, then the policymaker is going to implement the program. And if not, then the policymaker is not going to implement the program. And this is a caricature. We can debate how close it is to reality, but we think it captures something. And one of the issues that we have, or that we know we have with this approach, would be that the usual significance filter only accounts for sampling uncertainty. But the observational estimate that we get has a remaining observational bias, which we're going to call OB. And this bias is of unknown direction and magnitude. So observational bias is basically the selection bias is what you start off with. You do your best to get rid of it, but you still have a remaining observational bias. And we want to highlight that the true uncertainty, therefore, in your estimates can be much larger than the sampling error, which is captured in the standard errors. So there are two broad options that you have here. The first, and one that's argued for by a lot of people, is that you should abandon observational estimates and run a randomized controlled trial. This is because when you get your observational estimate, you just don't know how accurate it is. The second thing you could try to do is to be more honest about the true uncertainty by estimating the extent of observational bias. And that's what we're going to do in our project. And I want to highlight here that if we are more honest about true uncertainty in observational estimates, that will give us a better understanding of whether we need to run randomized controlled trials. Okay, so what's our project and what do we do? So as I said, our aim is to treat observational bias as an object that can be estimated. We can then use that to be more honest about uncertainty beyond sampling error. We can use it to evaluate different observational methods, and we can use it to understand when to run an RCT. How do we go about estimating observational bias? Well, we create a new large data set of imperfect compliance randomized controlled trials. And we can use that data set to estimate an observational bias in each of these RCTs. And we combine these estimates to work out what the distribution of observational bias is. Now, obviously, we're going to have to make some assumptions to do that. And I'm going to quickly give you a guide to the assumptions that we're going to make. Okay, so an overview of our methods. First of all, what is the object that we are interested in? So we're going to define a true causal effect of some intervention as beta true, and assume that it is the limit as n goes to infinity of an experimental estimator. So that is beta hat E is an RCT-based estimator. Now the estimator is going to be, as you'll see, either the local average treatment effect or the treatment on the treated. And so we're really making two assumptions here. The first is that the experimental estimator consistently estimates the policy parameter, beta true, and also that the local average treatment effect or the treatment on the treated is what the policymaker wants to know. And we'll discuss a little bit later on whether that's accurate. And so our question is then, what can we learn about beta true from a potentially biased observational estimate when we don't have this experimental estimate? Okay, so suppose that we have an observational estimate, and we're going to call that beta hat NE for non-experimental, and we have an estimate of its variance. And then we're going to say that theta is the observational bias, and again, it's of unknown direction and magnitude, so we're going to make the following assumptions. We're going to assume that the non-experimental estimate is distributed normally around the true parameter that we're interested in, plus the observational bias, and with some variance. We're then going to assume that this observational bias is drawn from a normal distribution with mean mu and variance tau squared. And this is really our key assumption. So we're assuming that there is a distribution of observational biases and that we can sample lots and lots of observational and RCT estimates to try to estimate this object, so mu and tau squared. So if we had estimates of mu hat, tau hat squared, and then the variance of mu hat, then under the null hypothesis that beta true is equal to 0, we would have an appropriate two-sided confidence interval that differs from your usual confidence interval in two ways, or three ways. First of all, we want to subtract off the mean bias. And second, we want to account for additional uncertainty. Some is true uncertainty in the sense that we have a distribution of biases, and those are never going to go away. And the second is that we aren't 100% sure what is the appropriate mu hat to subtract off here. And these are going to make the confidence interval wider. So this is our sense in which we're being more honest about how much uncertainty we have around the estimate that we produce from an observational study. Okay. So an overview then of how we're going to estimate mu hat, tau hat squared, and sigma hat squared. So the premise we have is that our imperfect compliance RCTs allow us to construct an observational study and estimates its observational bias. So we take an estimate of a from the same sample, a non-experimental estimate, and we subtract from it an experimental estimate in the same sample, and then we form an estimate of the observational bias. We're then going to assume that we can continually sample from a set of imperfect compliance RCTs that are exchangeable with a policymaker's observational study of interest. That is, that when we form this estimate, we do it many, many times, and we're going to assume that that comes from the same distribution of biases as the study that the policymaker is interested in. And the implication of this is that we can learn just by looking at many, many imperfect compliance RCTs. So then how are we going to estimate mu hat, tau hat squared, and sigma hat squared? Well, for each study, we calculate an experimental estimate, we calculate a non-experimental estimate, we try to make sure these are comparable, and I'll talk about that later. We then calculate the observational bias in each study, and we do some meta-analysis to recover to separate out what is caused by the true uncertainty, the normal distribution of the biases, from the sampling error inherent in the estimate of theta hat. Okay. So let's suppose you can do this, and you then can form these confidence intervals. As I said before, the goal then is to have these three things that we can do: be more realistic about uncertainty, evaluate different observational estimators, and understand the trade-off between RCTs and observational studies. So just give you a little bit of a sense of how you can go about doing that. So I'm going to show this same diagram that's on the left a few times. So on the x-axis here, you have a treatment effect. And on the y-axis, you have a standard error. And the red lines here are the usual confidence intervals. So in essence, the treatment effect has to be twice the size of the standard error to be considered to be statistically significant at our usual levels. So that's the red lines. The blue dotted lines then are the confidence intervals, taking into account tau hat squared and sigma hat mu squared. So this confidence interval at the bottom of this page here, where I'm assuming that mu hat is equal to 0. Okay. So there's some interesting things to note about this. They're all a bit obvious, but I do think they're interesting. The first of all is that uncertainty does not disappear as n goes to infinity in our observational study, as we're used to thinking. We still have the uncertainty around how much observational bias there is. Tau hat square will remain. The second is that these curves, the blue lines, are not linear. So observational bias is more of a problem in better powered studies. This is intuitive. If you have a very poorly powered study, your main issue is that you're poorly powered. If you have a very high powered observational study, your main issue is that you don't know the extent of selection or observational bias in the study. Tighter estimates of the extent of observational bias might be more useful then than a larger observational sample size. Fourth here, and something that's I think a little counterintuitive, although I don't know, is that if tau hat squared is small, that is, there's little uncertainty about how much bias there is, it doesn't really matter if there's an on average bias. When you look at our confidence interval, if you know the average bias is say 0.3 standard deviations and in a positive direction, you should just subtract it off, and then it won't matter at all. So really what we're interested in understanding here is how big is tau hat squared? How much uncertainty is there around how much observational bias there is in our observational estimate? The final thing is that non-significant effects can become significant because if mu hat is positive, for example, is negative, for example, then we could have a big, strong positive effect that we can't see until we do our adjustment. Okay, so that's being more realistic about uncertainty. The second thing is we can try to understand which observational methods are best. So these are two of the observational methods that we look at in the paper. I'll tell you more about what they are in a second. But you can see that even with infinite sample size, nothing inside these green tram lines can ever be identified. So if you have a true causal effect of the size that lies inside these green tram lines, you could never use an observational study to find it. That means how narrow these tram lines are is a reasonable good guess of how effective observational methods are. And here you can see that the right-hand picture labeled PLR, which is the double debiased machine learning method, performs better by that metric than WW, which is just a naive with and without estimator. And you could think about doing this with many different estimators. The third thing is you could try to understand whether an RCT is going to perform better than an observational study. When would you like to run an RCT? So let's take point A, and let's suppose the true effect is what the treatment effect is there, and you have a small sample size, which means you can't observe that true effect or test it using your observational study. Now, in that case, increasing your sample size is going to increase your ability to statistically work out whether that program has the negative effect implied. On the other hand, if you look at point B, it's never going to be helpful to increase your sample size in your observational study. You're always going to have a problem that even with an infinite sample size, the uncertainty around the observational bias means that you can't tell whether you have a positive, a negative, or a zero effect. There's a third point, C, which is the point at which a randomized control trial, which has the confidence intervals given by the red lines, dominates an observational study with an infinite number of observations. And it's interesting then to think about finding point D. We can think about how many observations do we need in a randomized controlled trial before it would dominate an observational study, even with an infinite number of observations. And we'll go through and talk about what we find on that in a second. So that's the hope from our method. Okay, so now I'm going to tell you about what we actually do. So I'm going to talk about the sampling and the context, the set of IC RCTs that we have and where we got them from. A few more details of estimation, although really not a lot of details of estimation. And then I'll talk through the results and offer some concluding thoughts and where we're up to with the project. Okay, sampling and context. So I don't know how many in the audience know, but starting in the late 1990s, we've had a huge increase in the number of randomized controlled trials in development economics. The 2009-10 Nobel Prize, for example, went to a group of people predominantly for encouraging people and showing that we can do these sorts of randomized controlled trials. This rollout is primarily facilitated by two organizations. The first is JPAL, the Jamal Poverty Action Lab, run out of MIT by Esther Duflo, Abhijit Banerjee, and a host of others. And the second is Innovations for Poverty Action, which was started around the same time by Dean Carlin, Annie Duflo, etc. And both of these organizations try to facilitate doing randomized evaluations in developing countries. And so what we've done is we've partnered with IPA and JPAL to access all their dataverses. And in total, we have 207 complete data sets from randomized evaluations. So from that data set, we're going to gather all the imperfect compliance RCTs, distinguishing between two types. The first are eligibility designs. This is where you have a treatment group that is eligible to get an intervention, and the control group is excluded. And here we're going to assume that not all of the treatment group takes up the intervention. So you're allowed to take a job training program if you're in the treatment group, but some people do and some people don't. And in the control group, you can't take up that job training program. And here we can get the experimental estimate, but we can also form an observational estimate within the control group by comparing those who take up to those who don't. The second kind of study is an encouragement design. Here we have a treatment and control group that can both participate in the program, but the treatment group, those in the treatment group, are given an additional incentive to do so. So for example, everyone is eligible to be in a job training program, but in the treatment group, we lower the costs of getting into that job training program. And here we can form an observational estimate in both the treatment group and in the control group. In total, we end up with 40 imperfect compliance RCTs. About 56% are eligibility designs, and the remainder are encouragement designs. Some facts about what these studies are that might be interesting. On the left, we have the country. As might be unsurprising given JPAL's origins, there are a lot of studies in Kenya, but there are also a reasonable number of studies in Uganda, some in the United States. We have a lot of poorer countries and just a few in wealthier countries. The main sector, we have a couple of agricultural RCTs, a fair few in education, a lot in finance. Dean Carlin is very represented in this data set, we'll see in a second, but we have also some political governance, etc. So those are what we're looking at. In terms of journals and authors, the papers are published predominantly in economics journals, many of them in the journal of the American Economic Journal of Applied Economics, which publishes a large number of randomized control trials. The editor was formerly Esther Duflo, but we have a set of things across different publications. As I said earlier, there are a number of authors that are very highly represented in this data set. For example, Dean Carlin has 11 trials. To some extent, this represents the fact that Dean runs lots of imperfect compliance RCTs, but predominantly this represents the fact that he runs a lot of RCTs and is committed to ensuring that his data is available on the Dataverse at IPA. Similar comments could be made about Pascaline Dupart and Esther Duflo. So then, how do we go about estimating bias? So, we want to have comparable estimates between our randomized control trials and our observational studies. So we're going to start with what can we estimate from the RCTs. And we know that with the usual assumptions, SUTPA, first stage, randomization, exclusion, and monotonicity, then the RCTs both estimate different kinds of lates. In the encouragement designs, we get the treatment effect for the incentive compliers. That is, for the people whose decision to take up the program is changed by the incentive. And we're going to call that late E, experimental late. In eligibility designs, we get treatment effect for those who are in the treatment group and who choose to take up. So we're going to call this the treatment on the treated in the experimental group, TOTE. And you could ask whether these are policy relevant parameters, and there's a debate about whether they are, which is sometimes a little bit abstract. And I think the team think these are policy relevant parameters in the following sense. If your goal as a policymaker is to decide whether you want to encourage people to take up a program, then you want the late. If your goal is to expand the program to more people and different areas, you want the treatment effect on the treated, ignoring external validity. So we think they're both policy relevant parameters, and it would depend on what you as a policymaker want as to which of these you would like to know. On top of that, we think there is no clear intuition as to why you would have a different amount of selection bias or observational bias in a late to a treatment on the treated. And as a consequence, we think the best initial assumption is to treat them as exchangeable. If I have evidence that late estimates have really strong selection bias, I should tend to think that treatment on the treated estimates also have really strong selection bias. And I don't see why you wouldn't think that, although we could test that in what we do, although we don't. Okay, so now we've got these RCT estimates, and we would like to try to create observational equivalents of these estimates. Now, our key assumptions here are going to be conditional independence and common support. Common support saying that we have some people in treatment and some control for all the key X's that are required to reweight to create an observational estimate. Then we can create non-experimental equivalents of our experimental estimands. So for example, in encouragement, we have late NE, and that is going to be, we have an estimator in a non-experimental estimator in the treatment group, beta NE treat. And then we have a similar estimator in the control group. And you can think that the difference between these estimates is caused entirely by compliers. In the control group, we have no compliers, but in the treatment group, we do have compliers. So the difference between them estimates something about the causal effect of the program on compliers. Now, like in other late estimates, we need to reweight these to get precisely the impact on the compliers. And we show in the paper that this is the formula for doing that. So for the encouragement designs, we can get an equivalent non-experimental estimate. It's much more straightforward for the eligibility designs because we sort of already know how to get treatment on the treated in a non-experimental way, so long as we have conditional independence and common support. Now, we can compare these two estimates to get their experimental and non-experimental estimates to get an estimate of bias. And that bias will be equal to 0 if we have conditional independence and common support. So to the extent that we estimate bias, it's a combination, or it could be caused by either a lack of a conditional independence or a lack of common support. But either of those say that you can't get back to the experimental or true effect just by doing your observational control methods. Okay. Now, we're going to have to use some controls in order to make our observational estimates. And what we do is we use the same set of controls every time we're estimating an observational or an experimental estimate. And we just use all the controls that are available to us in the data set. We dummy out all dichotomous variables, and we put in everything else linearly unless the original data set has decided, obviously, to put in interactions and higher order terms. I'm not going to describe them much here, but the median study has 407 covariates here. So at least in number, there are lots of covariates here. One concern, of course, would be that because these are randomized evaluations, perhaps people are not collecting the data that they would in order to control best for selection bias. On the other hand, those people who are running RCTs are collecting large data sets because they want to reduce the uncertainty in their estimates, so they have some incentives to do this well. Okay, so what then are we going to do in terms of estimators? Well, for our experimental estimator, we're going to implement Chernozhukov et al.'s double de-biased machine learning, and in particular their partial linear IV. This selects control variables, and our main goal in using this is to be hands-off. We, as the researchers, do not get to control how the estimator is created, and in particular, we can't pick and choose among different X's. When we're trying to study whether observational methods work, one problem we have is if we only have 1 or 2 studies, we can tailor the observational method to a known RCT outcome, and we want to avoid that possibility. For our observational estimates, we try 3 options, and you could try more. Again, our goal is to be hands-off. So we don't want to be actively choosing X's or methods, really. So we want things that are relatively computer-based and algorithmic. So the first thing we do is naive with and without. We just compare the people who took the program to the people who didn't take the program, and that's our estimate of the treatment effect. We also do a post-double selection lasso from the Belloni et al. Paper in 2014. And then we do the equivalent double de-biased machine learning method, which is partial linear regression. That's equivalent to the estimator we use for the experimental studies. And both of these 2 estimators, they're popular in the sense of automating your choice of X's in a study. Okay. So then after doing that, we create an experimental estimate, we create an observational estimate, we subtract the 2, and we have an estimate of the bias. So we've got a whole heap of theta hat S's, and we have some estimates of their variances. Now, the final thing we need to do is to make these in comparable units. So we make 2 normalizations. The first is a magnitude normalization. So all treatment effects are in standard deviations of the control. This is common in many areas of economics. So for example, if you're studying the causal impact of a teaching program on test scores, you tend to use standard deviations of the control. And a basic rule of thumb is that 0.2 standard deviations is a reasonably large effect. So we do that. The second is we need to normalize the direction. And what we do is we have people go through and code every outcome into whether or not it is socially desirable. And then if it's socially desirable, it has a positive coefficient. And if it's socially undesirable, it is a negative. So those are our two normalizations. Then we have a meta-analysis. And so a little bit more on what I said before. So essentially we assume that our estimate, theta hat S in study S, is created linearly. So we have a mean bias mu, and then we take a draw from a normal distribution, which has mean 0 and variance tau squared. And then we have some sampling error, eta S in the end. We can assume that eta S has a normal distribution because of the central limit theorem, which suggests that our estimator should be normally distributed. And so our main assumption here is equation 2, which again says that you are drawing bias from a normally distributed population, and that we can use the imperfect compliance RCTs to learn about this normal distribution. Now, given this model, it's well known that you can efficiently estimate this using restricted maximum likelihood. In fact, in the paper, so we don't just have one outcome variable for each study, we have multiple outcome variables. And so we account for correlation within the paper by using a hierarchical extension of this meta-analytic model. So I think I'm doing well for time. Good. Results. So a couple of caveats before we go into the results on RCT quality. We need the super assumption and the exclusion restriction to hold, because the spillover will invalidate both RCT and observational estimates. And exclusion would invalidate a lack of exclusion would invalidate the RCT estimate. We assume that these hold throughout because the authors of the papers do themselves. And essentially in the paper, we just provide a description of what the exclusion restriction is and what the intervention is. We think most of the time these should hold, but it is a caveat to what we're doing. Okay, now some data. So first of all, we can estimate the raw observational bias. This doesn't take into so the bias that we estimate is a combination of the true bias and sampling error. And these are that combination. And two things to note with this picture on the left is that on average, the bias that we find is close to 0. And that's true independent of the estimator that we're using. The second thing you might note is that the PLR, this is the double D biased machine learning estimator, is a little more narrowly, it has a narrower distribution, suggesting it's able to avoid a little bit of bias. On the other hand, the other estimator, P2SL, the Bologna et al. Estimator, has a very, very large variance or standard deviation. This I note down the bottom because in fact it has a lot of outliers which pull it out that you can't see in the picture. We can also try to have a little think about whether controls work. Do they do the jobs, whether observational estimators do the job that they're supposed to be doing? And so on this picture, we have on the x-axis the initial selection bias. That is, what is the implied selection bias from the with and without estimator. And then on the y-axis, we have the bias that results at the end of doing our best with these two methods to control for that bias. And the black line is a 45-degree line, and the blue line is a best fit line through these points. What we would ideally like is that the remaining bias is not related to this initial selection bias, so these blue lines should be horizontal. And you see that we're not doing an amazing job in getting rid of bias. An alternative way to look at this is that we have the observational estimate on the x-axis, and then we have the experimental estimate on the y-axis. And ideally, we would then like the experimental estimate and the observational estimate to be roughly the same, that is lying on the black line. And you'll see that the blue line, the lines of best fit, are not close to the black line, and PLR does better than P2SL. Again, these don't take into account sampling variation, and so we might think that we're biased towards finding this effect. With that in mind, these are the results of the meta-analysis, which should take care at separating out the true uncertainty from the sampling problem with the bias estimates. So let's have a look at these. So we've got the with and without estimator, we've got the double debiased machine learning estimator, and we've got the Bologna et al. Estimator. On average, consistent with what we saw before, there's almost no bias. It's not that estimates are systematically biased in favor of finding that programs are positive, and it's not that they're systematically biased in finding that programs are negative. None of these estimates are close to being statistically significant. The slightly mislabeled thing with a hat here is then the variance. Sorry, the standard deviation of the biases. And what you can see here is that these are really very large. And you can see that they differ across the methods. So the with and without estimator has a 0.3 standard deviation, the double debiased machine learning 0.2, and perhaps surprisingly, our third estimator actually increases the extent of our uncertainty, which means it's going to be not very effective. Given the size of these coefficients, it's fairly clear at this point that observational estimators are not going to be able to find treatment effects that are of large and important size. So as I said earlier, in the education literature, we often think of a 0.2 standard deviation impact as being large and important. And given the uncertainty shown here, we are never going to be able to see an estimate like that. Okay. So let's go back to our three goals. First of all, being honest about uncertainty. So these pictures are from our with and without estimator and our best estimator, which is the PLR estimator. And they show the same funnel plots that I showed earlier. The red lines are what you would traditionally think of as the confidence intervals, and the blue lines are our adjusted confidence intervals. Every single dot here is an estimate from an observational estimate from our sample, and it's those that lie between the blue and the red lines on either side of zero that are estimates that would have been statistically significant without taking into account uncertainty around selection bias. And you can see that quite a lot of estimates lie in those tram lines. And in fact, very few estimates lie outside once you take this into account. The second we can be, and the second thing you'll see here, of course, is consistent with what I've said before. The PLR estimate, or the double debiased machine estimate, has narrower bands. That would mean that if you have a very, very well-powered study and you use the double debiased machine learning, that's better than using the with and without estimator, because you will be better able to distinguish true treatment effects from zero. Second, we can think about RCTs versus observational methods in the way that I said earlier in terms of the power, the advantage that RCTs have, because we assume that they don't have any selection bias. So let's make a couple of assumptions. So we'll suppose that the variance of the outcome is 1. That means everything we're thinking about here is measured in standard deviation units. We'll assume that the bias, as we have throughout, is distributed mu tau squared. And we'll assume we have an RCT that assigns 50% of treatment to treatment, 50% of the sample to treatment, and 50% to control, and that we have perfect compliance. And then we can think about, for example, an observational study that has a tau of 0.05. Well, you would need an RCT with 1,600 observations in order to do better. That's the point at which The red line crosses the blue line here. It gets much better for the RCT as tau goes up. And if tau is 0.3, then an observational study is dominated by an RCT with just 44 observations. What do our estimates suggest? Well, mu, the average is basically 0 in our preferred estimate, the double debiased machine learning. But the tau plus our uncertainty around mu is large, something around 0.25. That means that a 64 observation randomized control trial is more discriminating than an infinite observational study. Now, this of course depends on this assumption that we can get perfect compliance. And of course, the fact that we can write this paper suggests that we can't always. And this is just a graph showing you how this changes as compliance changes. So this is our estimate that you need 64, I think, 64 observations for the 100% complier RCT to dominate an observational study. You need about 250 if you have 50% compliance, and you need something like 1,000 if you have 25% compliance. So with low compliance RCTs, with small sample sizes, then the observational estimate will tend to be more discriminating. It's interesting to think about how big these sample sizes are. I run a lot of randomized controlled trials, and we tend to have observations in the thousands. So I think that oftentimes we are running RCTs that would be in the space where they dominate the observational studies. Okay, so that's about it. And I've got some concluding thoughts before we finish. Overall, we don't think our estimates look great for observation studies. There are some caveats to this. Of course, randomized controlled trials may have their own biases. Randomized controlled trials may not be possible in some locations, and that may mean, or for particular programs, and that may mean that they are lacking in some external validity. Even so, we do think our results suggest that it's very hard to learn from observational studies once you take seriously the question of whether or not what we really know about the extent to which there is selection bias that remains after we do our best. What are we going to do next? Well, the key assumption here, I think, that people are not going to like is exchangeability. That is, all of the imperfect compliance RCTs that we collect are in some sense, the policymaker doesn't know which of these imperfect compliance RCTs are similar to the study that she would like to run. And many people are going to argue that that's not reasonable, and that in fact, researchers tend to know something about the direction and size of bias in particular settings for particular questions. And I think one thing that's very interesting to us is that, of course, is testable with our method. So there are new papers which go out and use online platforms to ask policymakers and researchers what they think about certain settings. And you could imagine taking our data set and describing each study and saying, what direction do you think the bias is going to be in this study? You can then test whether policymakers and researchers are correct about that. You could ask other questions. What would be key X variables to collect in this setting? We could try to understand whether people really do know and have prior information about the direction, size of bias, or how to control for it. And that's where we're going next. I think I've nailed the timing, so thank you very much.
Oh, thank you, Gharad, and thank you for sticking to the time. And so we do have one question. I think I'm reading it, as you're probably also reading it. It just came out, which is more of a comment than a question. It says, it's from Stephen. I just want to congratulate. Okay, so that's great. Excited to see this work coming out to fruition. For the IPA side, we'd love to collaborate with you on disseminating the finding from the study. I have to go to another meeting, so I'm sorry. Okay, so that's yes, we put more a comment, and I do have a few questions, so I will encourage people to write questions in the Q&A box. I I can ask a few questions of clarification, and but maybe you want to say something about dissemination. So I think this is Stephen is correct. This is a very interesting study, and it does have a number of implications for people using evidence from randomized controlled trial and observational studies. So what are your plans for disseminating and to making the study more public?
I think our first thing is to present. This is the first time? No, we've presented around a little bit, but I think the first thing is we just need to present it around. Is our interpretation of the results too strong? Do people really think this is a reasonable way of going about doing that? Because you know, if you take very, very literally the results, they do seem to be quite negative for observational studies, but there are obvious reasons why that might not be a desired conclusion. So I think we want to sort of make sure that we understand what we should be concluding, and the best way to do that is to get lots of feedback. And then I think, yes, obviously JPAL and IPA are the people through which we are thinking of trying to work to try and get the results out there. Does that make, is that right, John?
Yeah, maybe we should also mention to Steve at IPA helped us a lot with some of the early data collections project, which is one of the background for the context of that comment.
Okay, so still no questions. So maybe I will go with one or two questions. First, I think I have a comment more than a question. First of all, that it's about your conclusion when you say that the results don't look great for observational study, but I think people could have a different reading from what you presented when you show that observational studies have zero bias for a sample of study, for the sample of study you looked at. And normally the expectation would be quite the opposite, right? That that observational study will be biased. And so, you know, to show that the bias is zero, I understand the issue of the variance. We can talk about the variance that as well, but still finding no bias on average, it is, I don't think, I'm not sure you can say that's so negative overall, the results for observational studies on balance.
No, so I guess that we should emphasize how we think about this. And I guess you're right. So, and maybe we should talk more about this. So on average, there's no sense in which we're finding that an observational study would be biased in over or under adoption of any particular program. You take your observational study, and if it's positive and you adopt, and if it's negative, you don't adopt, then you know, there's no sense in which you're systematically over adopting or systematically ignoring things. And I think maybe you're right that that is a sort of something that we're learning that would suggest that observational studies, even though they're very noisy, they are not systematically doing the wrong thing. I guess our overall feeling was that once you've done what we've done, if you had phi under positive bias, you would just subtract it off. And so as a consequence, we thought we could correct that problem. And so when we found zero, we sort of felt like, to some extent, the problem that we thought we could really solve doesn't exist. But you're right, I think we should change the emphasis, or at least I should change the emphasis of what I'm saying.
And maybe I can jump in and add something, which is, there's a sense in which there's an opportunity here, because we have a lot of this remaining variance of the biases. So we find a lot of bias in individual studies. It's just sometimes they're positive and sometimes they're negative. And then there's an open question of how much of that could we explain if we had more information about the context of the studies. I mean, we've tried to use a little bit of contextual information from the data that we have. But I think one really promising way to go is to see if, for example, people who are active in the areas where these studies are conducted can tell us, well, we expect that this particular one will be positively biased, this particular one will be negatively biased, and that kind of information, which we think would be available to policymakers, may help a lot in shrinking that remaining variance. That's a hope that we have. It's untested as yet.
Sure. Still no questions on the Q&A, so maybe I can go with the follow-up questions on the variance. And so the question is, so I guess my question is better understanding the tau square, whether it's something that you actually, because I wasn't sure at some point whether it's something that were the values that you were showing or something that you were assuming or something that you had actually estimated. Because yes, because my question is, so you at the point you say that there is no way to reduce the uncertainty. So one thing is clear, right? So that's on average, observational studies are unbiased, but they have a larger variance. Okay, so that's the starting point. And you say there is no way of reducing that variance. And but I wasn't sure whether you were saying that within a particular study or across study, whether it's something, because you know, the alternative could people say, well, fine, we can do more observational studies, and then if we average across studies, then you
so let me narrow down a little bit.
Please.
So there are two sources in the way we set things up of uncertainty in the extent of bias. The first is tau squared, which we're assuming is a fact about the world, but I'll get back to that in a second. The second is uncertainty in our estimate of mu. That's the sigma squared mu. Now, the more IC RCTs, imperfect compliance RCTs you run, the smaller will become our uncertainty in the estimate of the mu. So in that sense, you can improve and you will learn. The second thing is we are assuming that the researcher has no information that would tell her which of the studies in our sample are best going to capture the bias in her setting. That's why we're able to say that there's this one distribution. Now, that may not be correct, and it may well be that she can say, no, actually, these 17 studies are the ones that are similar to mine, and you should throw away these 23. And then when we took at these 17, we may get a much lower estimate of tau for the set of things that she thinks are relevant. That's sort of the comment I made in the last slide that we're trying to work on. So those are the sort of two ways in which you could go about trying to reduce uncertainty. Both of those we think are interesting because they suggest a sort of method of trying to run imperfect compliance RCTs and understand why we get the biases we get in different settings, and then use those RCTs not as results in and of themselves, but as a method to narrow the uncertainty in observational studies. So you can imagine a world in which we've run enough RCTs that we really think that we do know how much what is going on with our observational estimates, and then we don't have to run any more RCTs after that. And we think that would be cool. Obviously, that requires a lot of RCTs to run. So is that clearer what the sources of uncertainty in the estimates are? Or not? Or have I not narrowed it?
Not entirely. So, but yes, please go. So, so that's your answer, or
I mean, you asked one thing. I think you asked, are the numbers that we were showing in the graphs, are they assumptions or estimates? And I think the answer to that is they're estimates. So the 0.25 standard deviation number that Gharad was showing on plots is our estimate of the additional variation that's coming from uncertainty about bias.
So we really are saying, if you believe this assumption that you can't distinguish between the studies in our data set, and each one is equally likely to be representative of the setting that you're interested in, then you really do need only 64 observations in your RCT for it to do better than your infinite observational estimator. Like, that really is what we think is the outcome here.
Okay, sorry, I have a question. Maybe it's a silly question, but is because your sample is 40 studies, so we want to be sure they understand this. Suppose you had 400 studies. Would the estimate of tau change or not?
Yes, so tau is obviously estimated with error. And that error will slowly go down.
Yes, but you expect tau to go down with sample size or not?
No. No, it should be unbiased, I guess. And so in some sense, it's our best guess at the moment of what we would get in that larger study. What will go down, well, you would have to change our method by saying, can we understand within the set of larger studies, which ones are more representative of, say, agricultural experiments, and which ones are more representative of education experiments, etc. Then you could try to do a better job of narrowing it down. But at the moment, it's our best guess of what you would get in the larger studies. What would happen as you get more and more studies is the standard error on the mu hat, the average, would shrink. So that will bring in those blue lines a little bit, although actually not that much, given what we're currently finding.
Okay, got it, I think. Still no questions. So I guess I'm going to ask one final question, then we can close. And that goes a bit to the context, and also I think some of the comments that we got from the reviewers when we were working on editing this paper. So you're looking at the RCTs as being unbiased, but surely that's an assumption, right? So some of the RCTs will not be perfect, and so they might be biased to start with. And in fact, I think, so you're considering all the study as being all alike, but some of them would be, even within RCTs, there would be studies that, you know, the way they have been implemented or the characteristic of the context, some will be unbiased 100%, and some others will have some risk of bias. And
yeah, so there are kind of two issues here, which is that we know these IV estimates are biased in some sense in small samples. That's why we're kind of assuming that they're consistent, not biased in small samples. So there's sort of a technical issue here. But then there are sort of the much more practical and probably larger issues. So for example, if we don't have double blinding in an RCT, do we really believe the results? I think that's exactly right. You have to sort of believe that the RCT does have this sort of gold standard standing. Again, I think that, you know, and we don't have a lot of studies here, and it will be a long time before we have many more, but we do think that the research agenda of saying, okay, well, we could try to think about studying that and trying to understand. So you could ask again, which of these RCTs do you think is going to be biased upwards or downwards? And you can think about trying to understand whether that is accurate and whether you can use that information at all.
Yeah, because currently I think your sample is probably too small. We only have 40 studies, but in principle, in principle, you could have a risk of bias assessment for within RCT and to make some.
You can do all the sorts of things that Cochrane would like to do.
Yeah, exactly, that sort of thing.
And those all make sense in this setting.
Okay, so that's I think time is up, 1 hour, and so I'd like to thank you and for this very interesting study, Gharad and John, and thank you for people for attending. I think Stephen was right. So you need to think a bit more about how to, not just to think about conferences and paper publication, but something more, other ways of trying to disseminate your work and make it public. So just to thank everyone, and also to say that this was the last of our webinar. So to thank everyone who's been attending webinar seminar, CEDIL webinar over the last few years. And so that is the last. And but I think I'm glad that we close with a very interesting project. And so thank you again, everyone. And have a good rest of the day.
Thank you very much.
Thanks, Eduardo. Big thanks to CEDIL for funding this work.
Yeah, thank you very much.